Hey y'all, so in the last couple of weeks of January 2026, we had some intense cold weather come through our part of Texas. Schools were closed for most of the week, and I read that the Dallas Mavericks got stuck at the tarmac at the airport for a while. I got iced in myself for a few days, and so I decided to complete this YModem project I had been working on. Last fall, I'd been reading about YModem, and I had been testing it between my modern PC laptop and an old 486 system, using terminals like Telex, QModem, Connect, and Telemate. While on the modern PC side, trying HyperTerm, Zoc, and even old HyperTerminal under Windows. Alright, so during that week of being iced in, I came back to my YModem project, and I got it working in BASIC on the X16. I'll link the code in the description. I'm using the Zoc terminal on the PC side, which notice I have it set at 1200 baud. And notice I can pick multiple files. Once the YModem upload is specified, the terminal is now waiting for a continue command to indicate when the remote session is ready. So we'll flip over to the X16 and run the basic program. At the start of this YModem receiver, I do a 5-second drain to make sure the first in, first out buffer of the UART is flushed out. There could be leftover activity from a prior test session, so this just drains all that out. There's nothing sacred about the 5 seconds, it's just what I chose. Okay, the transfer is started, and I'll pause about halfway through this header block. Alright, the first part here is what port the X16 is using to talk to the serial UART. That's not the only address the hardware uses, it's just the first address of a series of about 8 registers. And they function differently depending on whether you're writing to or reading from them. This is all fairly standard UART stuff, nothing X16 specific, other than the set of ports they elected to latch to. Next is the uppercase C letter. The software running here is the file receiver, but recall RS-232 is bidirectional, so there are a few signals that have to be sent to keep the transfer in sync. And that first signal is the letter C, to signal to the sender that I'm ready to start the protocol. C here means initiate CRC mode. Next, the system uploading the file passes this 3-byte block header. The first byte is the upcoming block length. A 01 indicates 128 byte blocks, while 02 indicates 1024 byte blocks. The sender can technically alternate block sizes throughout the transfer, like at the very end they might dial down to 128 byte blocks to gain a little efficiency. Or for very slow or memory limited systems, they might just stick with 128 byte blocks. Following that is the block count and then the inverse of that count. They should both always add up to 255. Now with 1 kilobyte blocks, you'd think this would limit the protocol to 256 kilobyte files, but no, these block counters just roll over when they reach the end. And that's fine, they just help keep the sender and receiver in sync. If there's any momentary signal corruption, and these don't add up to 255, then the receiver sends a NAC signal to try the block again. Alright, next up, the 4: here is just some debug output that this is phase 4 of my code, which handles receiving the full block of data. It echoes back out the expected block counters and expected byte length of the block. Now we get to the main interesting part, which is the first block known as the header block, and contains the file name, file length, timestamp, and other supporting data. In this test run, the first file is a 0-length file, so the sender here just passes the file name. I'll show a more complete header example later, but the main thing is, this is how the receiver gets the file name, which is a null terminated string. Alright, now we'll finish out the rest of this block. Even though we're at 1200 baud, interpreted basic is so slow, plus we have debugging outputs enabled, we really only stream with a throughput of barely 110 baud. Some people can literally type faster than that. Now for some fun, we'll repeat this dissection using the serial analyzer. I'll play it at real-time speed first, then we'll go back and play it slower. Okay, now again at 1/5 the speed. DTE is the receiver, and DCE is the sender that is uploading the file. Okay, see that long pause here? That's important in a moment. First we get the header like we talked about, the 3 bytes for the block size, and the block counters that sum to 255. Then we get the first part of the file name. This data is flowing through a tiny 16-byte buffer of the UART. I have that buffer set to 8 bytes because on slower systems like the 8 MHz X16, you kind of need breaks for the control flow signal handling. I call this a runway. There is room for 16 bytes, but we trigger flow control early, so a few bytes can bleed over and still be okay. It's fun to imagine data having velocity, and the buffer is like a railway turnoff that can only fit 16 cars. It takes time for the "hey stop" control flow signal to propagate, so a slower system is like having heavier train cars. Anyway, from this display, we can't know how many bytes have already been pulled off by the receiver, but you can see here RTS has triggered before 16 or even 14 bytes. RTS is request to send, which toggles to indicate the buffer is past the designated threshold. Looks like 1 byte even trickles through while RTS is flipped. The receiver here is basic interpreted code, so about as slow as we can possibly get. That code is writing these received bytes into banked memory of the system, so there is a loop involved that takes time to parse. When it finally comes around to read more bytes out of the FIFO buffer, the RTS flips again and more bytes flow. In this case, it's just the final byte of the file name followed by the null character 0. After getting all that block data, the main question then is, do the local and remote CRC values match? The formula for this isn't super complicated. It involves some bit shifts and XOR operations. I'll post more specifics about that in the description. But after the block of data, the sender sends what its value of the CRC should be, and locally we're accumulating the CRC as we're receiving bytes. If they don't match at the end of the block stream, a character got dropped or something got corrupted in the exchange, so the receiver would send a not acknowledged signal and the block would get repeated. In this case, the CRCs do match, so for debugging, the code here repeats the file name and link to make sure all that got parsed correctly. For the first header block, the receiver sends an ACK, followed by an uppercase C again. This means the receiver parsed the headers, accepts the file name, acknowledges the full block was received correctly, and requests to continue the transfer. Because it is a 0-byte file, the sender knows there is nothing left to transfer, so it responds with an end of transmission indicator. If there was more data to be transferred, the sender would increment that block header counter and start sending the next block of data right away. I'll show an example of a data block in a moment. For now, I'm going to let this transfer go at regular speed, and we'll just watch it and transition through a few different perspectives of that transmission. Okay, let's pause here. The data's been streaming for a while and I noticed something interesting. Between each of the RTS flow control signal transitions, they are all 8-byte groups, so that shows me that the 8-byte threshold I set for the UART is working. At this slow speed, we could probably increase it to the full FIFO capacity, but that's neat to visually confirm the setting. Alright, a few files in the batch set have been completed. Let's take a look here at a more interesting header block. We have the file name up front and is null terminated as expected. If the file name or its path ended up over about 120 characters, the protocol could set the header to a 1 kilobyte block instead. The remaining YModem block header fields are all terminated with an ASCII space character. These include the byte length, the date, mode, and serial number. Anything after that is optional. These values are all in ASCII decimal, except for the time field is specified in octal. I noticed at the very end of the header block, Zoc populates the total expected block count. This is probably just leftover debug info, which is fine in the header block and ends up getting ignored. Okay, skipping a few blocks later, this is a data block on this same file being transferred. Notice it is 6 blocks in, or about a third of the way of the total file length, and the block count and the inverse correctly sum to 255 decimal. The only other interesting thing here is that at the end of the block, the receiver sends a single ACK response. The uppercase C is included only for the starting header block. Okay, we're now at the last block of the last file in the batch. File lengths rarely align perfectly with block sizes, so the final block is padded to the block size using null. The header block informed the receiver of the actual file length, so part of the receiver's job is to manage the file system to crop to that specified length. In this case, the file is 2,112 bytes, so this last block contains the final 64 bytes of the file. Now the question is, how to gracefully indicate the end of the batch sequence. YModem does this by sending another final header block with a blank file name and 0-byte length specified in the header. This results in the computed CRC also being 0, and the receiver now knows that the batch is concluded and no more files are coming for this session. Phew! We've covered a lot of details here, so now after this brief intermission we'll crank up the speed. Alright, so during this past winter, I molded the basic code over into a C version. The basic version was always intended as a slow motion model of the workflow. So this next part is just a demonstration of that C version running on the Commander X16, showing that it's compatible with a variety of other terminal systems. I use a 286 with MS-DOS, then OS2 and Windows 95, and then conclude with how it performs using a modern PC. I won't do a walkthrough of the code, but the intent was to structure it more for portability and understanding, rather than for maximum performance. Okay, first up is using this Compaq 286 SLT from 1988. Its monochrome LCD is weak, but pressing Ctrl-Alt flips it over to the color VGA output. The terminal software here is a version of COMIT from around 1991. It has this odd menu system that you access by pressing the / key. This version only supports up to 57600 baud, which was plenty fast enough back in the modem days. You prepare to batch files by first tagging them in this Files selection menu. And down here I can review that set of tagged files. Now I go over and prepare to start the upload. Then on the X16, run the YModem receiver software. Alright, now the file transfer is started. The first couple of files are small. While waiting for the remaining files, here's a demo of how the VGA output can be altered by pressing the Ctrl-Alt and greater than key. So despite the low baud rate, the throughput here is only about 2300 bytes per second. But that's already about 3000% faster than the basic version. Next is Procomm Plus, which is famous for its little whistle noises during menus. Here's an example again of flipping the VGA output on this Compaq 286. Procomm does support 115/200 baud, but besides the baud rate, there are two other important settings. One is to make sure the hardware flow control is enabled, and the second is to ignore carry detect during file transfers. Okay, with Procomm here, the batch can only be a file spec, like star.exe. It doesn't have a file tag or file selection dialog like COMIT did, or at least not one that I could find. Like before, after the upload is started on the host, then I flip over to the X16 receiver side and start up the download software. But first I need to adjust the baud rate that I'm using, which this little loader utility helps do that. Alright, I'll let this file transfer go for a little bit. So after letting this settle for a few file transfers, the throughput ends up at around 7400 bytes per second. Alright, so all of this was a perfect excuse to fire up my OS2 ThinkPad. The default serial driver from IBM only supports up to 57600 baud, since that was adequate for modem users even during the mid-1990s. There are third-party serial I/O drivers that can increase that limit. The bonus pack for OS2 includes HyperACCESS Lite, so I'll just use that included software. But it is a light version that doesn't support batch transfers, just single file only. The throughput rate here is about 3,800 bytes per second, but again, third-party serial drivers or high-speed PCMCIA UART adapters can improve on that. And here's a quick check that the file was received on the X16. This next system is a Gateway Solo 9300, one of my favorite Pentium 3 systems from 1999. Typically, I avoid Gateway stuff, but compared to their earlier Color Book and later 9500 series, these 9300s are fairly well built. Okay, Windows XP could be installed with a terminal program called HyperTerm. And like the OS2 base terminal software, it doesn't include batch file support either, just single file. But at least it does support 115.2 kilobaud out of the box. In multitasking environments, larger virtual serial buffers became essential. For MS-DOS and DeskView, we used Fossil drivers for this. Okay, I'm looking for a large sample file to try here. Okay, here, let's just use export exe. Okay, I've set up the sender, and now to run the receiver like before. Alright, the transfer is just about to finish. There it goes. And now to verify that it got received. Okay, stick around. I have one more special thing to show in this final segment. First, this is Zoc terminal software under Windows 11, and I'm using a standard USB serial adapter to transfer a batch of test files at 230.4 kilobaud. The throughput here reaches about 12,000 bytes a second. I've gone faster with this same receiver C code, doubling that to about 24 kilobytes per second, but that was using a higher quality cable than I have here today. The special thing I wanted to show is that I've also implemented a YModem Batch file sender using C#. So now I can transfer a batch of files from the command line, and the performance is comparable to what Zoc achieves. I'll have a link to this also in the description. So that wraps things up here about YModem. The interesting thing about YModem is that it's far better than XModem, but still primitive enough for many 8-bit systems to implement. The CRC lookup table only uses 512 bytes, whereas ZModem uses a 32-bit CRC. We've also found that YModem typically outperforms ZModem across variable speed wireless connections. So for instance, if you have two devices connected using a Wi-Fi modem, you might find YModem provides consistently higher throughput. Alright, thanks for watching.